Very good afternoon to all. It is my great pleasure to welcome all distinguished speakers, HODs, faculties, and dear students to our 5 days webinar titled From Tiny Atoms to Solid to Cosmos, the Quantum Aspects. This webinar is organized by Department of Physics CT in collaboration with IIT Bhubaneswar. It is high time that during this current pandemic, we all refresh our knowledge of current happening in different areas of physics. I am grateful to all eminent speakers who accepted our invitation and are here to share their knowledge with all of us. In this inaugural function, it is a proud privilege to invite Professor S.M. Yusuf Sir, Director IOP, as chief guest for today's function. Sir is also Associate Director Physics Group at BARC Mumbai. He is Dean Students Affairs at Homi Bhabha National Institute, BARC Mumbai. He is also Convener, Board of Studies, Physical Sciences, HPNI. He has taken many more responsibilities as Vice President, Indian Physics Association, Vice President, Indian Crystallography Association, Vice President, Material Research Society of India, President, Neutron Scattering Society of India, and many more.
Tiny atomic to count.
He has published nearly 300 research papers in many international journals. I welcome Sir to this inaugural function. I welcome Professor Antarami Mr. Sir, State Project Administrator, SPIU. He is a dedicated academician, professor in mechanical engineering at IGIT Saram and director of that institute. His inspiration and support helped us to conduct many programs under TechIP. I welcome you, sir, to this inaugural function. I welcome Professor P.K. Patra, sir, Principal CET. His constant inspiration, kind support, and guidance helped us to conduct such programs. Under his leadership, the college is accredited with A grade by NAAC and 4 undergraduate programs are NBA accredited. College become an autonomous college under BPUT. Heartily welcome you, sir, to this inaugural function. I welcome Professor N. Acharya, sir, Coordinator PCM. He always encourages and supports for conducting such program. I welcome Professor P.K. Parida, sir, Coordinator TechIP. His valuable suggestions and kind support helped us to conduct webinar under TechIP. I welcome Professor Devakant Samal, sir, Coordinator IOP. His expertise, support, and suggestions helped us to conduct this webinar in collaboration with IOP Bhubaneswar. Once again, I welcome all speakers, HODs, faculties, and students to this webinar. I am sure that we all will have fruitful and rewarding exchanges in the next few days. Title of the webinar, From Tiny Atoms to Solid to Cosmos, the Quantum Aspects. The program aims to enrich and refresh the research activities happening in different areas of physics, such as particle physics, solid-state physics, and cosmology. In particular, the quantum aspects of recent advancements in spintronics, superconductivity, magnetism, semiconductors, black holes, dark matters will be enlightened by eminent speakers of respective research fields. Furthermore, the technological importance of such fundamental research work will be covered in the lectures. The program will certainly enhance the knowledge of faculty members and highly beneficial for students. I am delighted to welcome all distinguished speakers who have taken time out of their busy schedule to be part of the webinar. All eminent speakers for this webinar are from various reputed institutes. Professor S.M. Yusuf Sir, Director IIT Bhubaneswar, Professor Ajit Mohan Srivastava Sir, IIT Bhubaneswar, Professor P.S. Anil Kumar Sir from IIC Bangalore, from Professor Debabrata Goswami Sir from IIT Kanpur, Professor Devakanta Samal Sir from IIT Bhubaneswar, Professor Sanjay Kumar Swain Sir from Niger Bhubaneswar, Professor Kartikeswar Senapati Sir from Niger Bhubaneswar, Professor Chandana Ratha Madam from IIT BHU, Professor Niharika Mahapatra Madam from IIT Bhubaneswar. I welcome all speakers to this webinar. Now I request Professor Devakant Samal sir, the coordinator from IOP, to address the gathering. Sir, please.
All right. Good afternoon to all of you. So let me see. So Professor Yusuf is joining us soon with us.
Sir,
Yeah,
will
can you hear
join
me?
us. Yes,
Okay.
yes, audible.
So respected Professor S.M. Yusuf, though he is not there, Director Institute of Physics, and Professor A. Misra, State Project Administration, Professor P.K. Patra, Principal CET Bhubaneswar, Professor A. N. Acharya, PCM Coordinator, CET Bhubaneswar, P.K. Parida, TUQPI Coordinator, and convener for this program, Professor B. Ojha, and other dignitaries who are participating on this online webinar, invited speakers, and the participating faculty members and the students. I'm really honored to welcome you all to this webinar, starting of this webinar today. As you know, the title of this lecture series or this webinar is not very focused title. It is rather, as you see, it ranges from tiny atoms to solid to cosmos. Unraveling the quantum aspects. When I was discussing with Professor B. Ojha, the convener, then they told me that they want to put a very broad topic so that because there are many MSc students and there are many BSc students, they are not specialized now because they are now grooming up now. So I thought maybe it is a good idea to have a broad topic where they can have a different perspective of physics research. They can because they are not specialized into a particular area of physics, so that they can have a smell, they can have a taste what kind of physics research is going on across various branches. So that's what the topic is, very broad, but it covers most of the things, because you can see here that is why you can. Yeah, I would request to please switch up the audios because it is giving a background sound. Yeah. So this is what so we have very distinguished scientists speakers with us. They have a very illustrious career. You will see when they will be introduced to, when they will be giving their talk in this webinar series. And I'm pretty sure that their lectures during this webinar or during this lecture series will be highly motivating and inspiring to the young students, faculty members, and researchers. And I'm very glad I was going through this little bit leaflet that is prepared by this Professor B. Ojha about this program, and about little bit history about the CET and how the CET doing. I'm very glad to know that many of the students, because in physics, who are graduating there with the master degree in physics, they are grabbing the PhD position in some of the best institutes in India. That's a very good thing, because I would tell, when I was a student in Utkal University, at that time mainly people think that maybe only Utkal University students, those who are pursuing physics in MSc, they are going to other institutes for doing research. But this was when I was studying my MSc, I'm talking about 2002. So it was not the case, but I'm very glad that from CET also, now people are clearing their whatever the GATE or JRF, and they are able to grab their PhD position in a various good institute in India. That's a very good push of news. Just I was glancing through the booklet, that leaflet, and I'm sure that such kind of lectures will not only help them, the young students, in learning various aspects of physics or exposing them to various areas of physics, but definitely this will make them more curious to pursue the career in physics research. So that is what it is. Not only that they will understand many things from this webinar series, but at the other hand also it will motivate them. It will make them more curious to have a this research career in physics. So I highly appreciate the efforts put by the faculty members of CET, Principal CET, TUQIP coordinator, and to many more who are involved in this program. And my sincere regards to go to Professor Ojha, so under whose leadership the program is being planned. And I think all the team members who are working, we had a WhatsApp group. So sometimes we give suggestion, but actually this, whatever you see, the preparation of leaflets and other things, the details has been done by these members, the team members, particularly this Dr. Rakesh Singh and this Jai Krishna Khatei. So my sincere thanks goes to them, because with their support, this has been successful. At least they have put a lot of efforts. Finally, from Institute of Physics side, I would like to thank Professor Yusuf, Director, Institute of Physics, for officially approving the IOP participation in this webinar, because that is what he always encourages. So when I approached him that Professor Oja approached me that can IOP participate here as in collaboration, then I requested Professor Yusuf that this is what Professor Oja has talked to me, so could you kindly approve it? And he was very happy to approve it. So I must thank him for approving IOP's participation. So IOP is in a way involved in this program. So with these few words, I will not take much time because you will come to know when the lecture session starts, you will know more about the speakers, the invited speakers. So with these few words, I once again welcome you all to take part in this webinar and explore various research activities or various direction of physics that is being pursued at the recent time. Thank you very much.
Thank you, sir, for your valuable suggestions. Now I request Professor P.K. Parida, sir, Coordinator TechHub, to address the gathering. Sir, please.
So good afternoon. Hello, Madam audible?
Yes, audible.
Good afternoon to all. Respected Professor Yusuf sir, the Director IOP, and the respected Antoine Mishra sir, the Project Administrator, TechHub of SPI Odisha, and the respected Professor P.K. Patra sir, Principal CET, and the respected Acharya sir, and the Coordinator and the Convener of the program, Professor Oja, and Professor Samal sir, and the other participants of the Department of Physics, and the other HODs and the professors present in the online mode. This one is the 7th online program conducted by CET under TechHub 3. So the TechHub is the Technical Education and Quality Improvement Program. Is the World Bank project implemented by the MHRD, Government of India. And we are the institute in Odisha, beneficiary of TechHub 2 and TechHub 3. We have successfully completed the TechHub 2 program, and the TechHub selected for TechHub 3. And under TechHub 3, there are 3 different components are there. The procurement of different equipments, a good number of high quality equipments we have procured under different departments, the different labs, which are the very valuable for us, like a state funded institute, where is the high budget equipment, procuring the high budget equipment are very difficult. We are procured through TechHub 3. And also under academic, we have conducted around 16 number of faculty development programs, workshops, and seminars. And in the online mode, recently, within the last 3-4 months, around 6 programs we have completed, and this one is the 7th online webinar in that series. So then other activities we have conducted under TechHub 3, we promoting our faculty members for their research and providing the seed grant. 16 young faculty members, we are provided the seed grant. We are encouraging the faculty member participating in different programs at IITs, IIMs. And by this way, through the TechHub program, we are enriching both academically and infrastructure-wise the institute. The rest is regarding the program. So since that is a very, as the Samal sir told, it's a very high level lecture series, and which is we are, and I am as a mechanical engineer, the ignorant about the program. So I think the list of the speakers are very high level speakers from the very reputed institutions, and I hope and I welcome all from the CET as a TQ coordinator, and wishing all the best for the organizers and for the participants. I hope within these 5 days, they must gather the knowledge and the idea so for their future research and the future study. So thank you all, and thank you, madam. With this,
Thank you, sir, for your valuable suggestions and assistance. Now I request Professor A. Acharya, sir, PCM coordinator, to address the gathering. Sir, please. Acharya, sir, A. Acharya, sir, are you present? Please join us.
Madam, is it present? Otherwise,
Yes,
you can
yes.
have.
Is it audible? Is it
Yeah, it's
audible?
audible.
Is it audible?
Yes,
Hello?
it is audible. Yes, it's
No.
audible.
Audible, audible.
There is some net problem. I was present in the principal's office, but some net problem now it is connected. So very good morning to all the dignitaries for this program, that is from tiny atoms to solid to cosmos, the quantum aspects. On behalf of the CT and also on behalf of TQIP, I welcome Professor Yusuf, the chief guest for this inaugural session. In addition to this, I also welcome Professor Mishra, the state project administrator, TQIP, our beloved principal, Professor P.K. Patra sir, and TQIP coordinator, Professor Parida, and the convener of this program, Professor Oja, dignitaries from IOP and also from IIT Bhubaneswar. So as Professor Parida has already told that this is the 7th program that is under virtual meeting. So we have conducted a lot of this virtual meeting, which will be beneficial not only to the students, but also to the staff members of the Department of Physics and also other science and engineering departments. And this is also one of the best mode of enrichment of knowledge nowadays during this COVID-19 period. And I welcome to all the other dignitaries who have not joined, but they will join later to deliver their address. And on behalf of CT, Department of Physics, and on behalf of all the science department, so I welcome all of them. And also I request all the students to interact with all the dignitaries during their talk, and also they try to gather as much knowledge as possible, because this type of opportunity they will not get every time. So this is one of the very beautiful opportunities, so that they can interact also in the virtual mode. And in this way, the bonding should continue with the Department of Physics, so that not only we have to limit ourselves in the faculty development program during this 5-day period, but we can continue and we can move to this linkage to the next level. Either we can have some sort of collaboration, or in sort of for curriculum development, or including some research aspect also. So lastly, I thank all the dignitaries for accepting our offer, and thank to the convener and to all the faculty members of the Department of Physics to nicely arrange this program, so that this program not only beneficial to the student but also to the faculty members. So I thank all of them. Thank you.
Thank you, sir, for your encouraging words and support. Now I request Professor P.K. Patra, sir, Principal CET, to address the gathering. Sir, please.
Yeah, very good afternoon. I heartily welcome the chief guest, honorable chief guest, director of IUP Physics, Bhubaneswar, and also Professor Antarjay Mishra, SPA, Odisha, and the coordinator and dignitaries, those who have from IUP Institute of Physics, and HOD Madam Dr. Bodhita Oja, and all the faculty members, those who have joined, and also the students, my dear students. It is a good occasion where the student, faculty members, and staff can enrich themselves for the benefit of the institute, for the benefit of themselves, and also for the benefit of research and publication, patent filing, etc. So through TQIP, we have been promoting this type of activities. I thank to the organizer, the Department of Physics, jointly with IOP, Bhubaneswar, for organizing such a good topic. And also we hope definitely the student, faculty member and staff will take the benefit, and there will have a mutual cooperation between IOP and CET Bhubaneswar. Since we are located at Bhubaneswar, IOP is at Bhubaneswar, will take the help of in developing research activities and also mutual collaboration in projects and filing patent through this app. And through this is the best method where we jointly cooperate with each other. For your kind information, we have already a Center of Excellence in Artificial Intelligence where the students are doing very well. It was well inaugurated on 23rd December 2019. Almost 1 year is going to be, but the result is very good because it is through the Tech Mahindra, and they are getting a good work. So similarly, I would request the director and all the faculty member and staff of IOP, the scientists, let them join hand with CET Bhubaneswar so that we have a mutual benefit so far as R&D, project, patent filing, PhD guidance is considered. Under autonomous system, we have started the PhD program, and also I request that IOP or any good institute to join hands with us. They can be the co-supervisor and also can be the supervisor if the circumstances needed so much, so that the R&D activities can involve both students, faculty member and staff. Because this type of workshop will definitely, or faculty development program will help the student and faculty member in a great future career. Let take some 5% or 10% gain of this 5 days program. Let the students, faculty member get good thing, good output. Because under autonomous system, my aim is that we should incorporate those outcome based into our syllabus so that the integrated MSc Physics and also 2-year MSc Physics students side by side, the faculty member and staff can take the best help. So my sincere request to all the students, faculty member and staff, take the best help of this collaboration of IOP as well as CET Bhubaneswar and make it a great success so that the R&D activities, project, doubt clearing, and patent filing, PhD guidance, etc. will improve. As a result, both will grow together. Like we have joined hands with ICT Mumbai Institute of Chemical Technology, where they have started a good work. Their faculty members are taking classes in some of the selected subjects, and we are jointly applying for the project and R&D activities, PhD guidance also. So ICT Mumbai and also Tech Mahindra COEI, and in future we have selected another 2 more COE to be established in CET. So it is only because of the cooperation from student, faculty member and staff and CET as a whole, we live in a single family where the head of the institution is the head of this family, and we have to cooperate with each other. So I thank the Department of Physics and the IOP for kind acceptance of this joint faculty development program or workshop for 5 days program. Hope this will take to the greater height, and in future we will have a joint collaboration with IOP Bhubaneswar. I wish this conference, this workshop, this FDP be a great success, and once again heartily welcome. And we are fortunate on behalf of all the student, faculty member, staff. We are really obliged to the director of IOP, Professor S.C. Misra, Professor Director of SPA Odisha, as well as all the faculty members and staff of IOP as well as CET. Thank you all. Thank you. I hope this will be a great success. Thank you all.
On behalf of organizing committee, I thank you, sir, for your kind support, motivation and guidance. Now I request Professor Antarami Misra, sir, State Project Administrator, SPIU, to address the gathering. Sir, please.
Am I audible?
Yes, sir.
Am
Yes,
I
sir.
audible?
It is audible. Yes, sir. Yes, sir.
Okay, thank you. At the outset, I have the pleasure of conveying my heartfelt thanks to Madam Babita Ojha, who has contacted me on one fine morning and asked me to come over here. I immediately told that probably I am not the right person to be here, because long back we have read physics. Beyond that, I have never seen a book of physics so far. Anyway, I accepted the invitation. So, Madam, I am thankful to you to be with you, because I am an engineer, basically a mechanical engineer, and without the best knowledge and a sound knowledge of physics, chemistry and mathematics, one cannot be a good engineer. Or engineering is nothing but the application of products that is coming out of physics, chemistry and mathematics. So I can say that it is the bedrock of engineering. And I have the audacity to welcome and convey my regards to Professor Yusuf, who is here as a chief guest from Institute of Physics, our respected principal, Professor P.K. Patra, Honorable TechCube Coordinator, Dr. Parida, and respected Nodal Officer Finance of TechCube, Dr. Achyut Acharya. And I am trying to recollect the names. So far, whatever I have remembered, then Professor Devakanta and the coordinator of this event, Professor Ojha. I am thankful to all of you. In fact, the topic which has been chosen, it's starting from atoms to wide application and development of materials, what I feel, with application of different kinds of loadings and process. And I was going through the topics. Certain topics could come into my mind, but certain topics, it just went out like a bullet over my head. Anyway, what I would like to mention here, that the demand for stringent materials is coming up throughout the world in a very big way, because the technology is changing in every twinkling of eye. Researchers are quite busy for developing excellent materials, adaptive materials, and as engineers who are concerned, we are now more focusing on nanomaterials as well as quantum tunneling composites and set memory alloys, smart materials, because that smart what has entered into our everyday life. We can go for a smart building, we can go for a smart kitchen, we can go for a smart mobile phone, or we call it as a smartphone. So all these things are coming in a very smart way for developing smart materials, smart products. I hope, starting from the atoms to the molecular structure and then going ahead up to the extent of developing a material with help of quantum mechanics will definitely help the researchers to go ahead as far as development of materials is concerned. Superconductivity is one part of that material, and superconductors are very much essential nowadays, and everybody is talking about a digital world, digital teaching, digital everything, digital examination online. The way you are conducting today, because of all of you, the fundamental scientists, I say, physics, chemistry, and mathematics, because of you, we are now able to do something. We can get a computer, we can get a laptop, we can get a smart mobile phone, and we are able to communicate with latest information technology that is available. Now, further we have gone ahead with artificial intelligence, robotics, as well as machine learning, cyber security, Internet of Things, and so on and so forth. But I would like to say that this cutting edge technology is nothing but a tool. Unless otherwise you are having the fundamental aspects of physics. If anybody hits my head from left side, my head will go to the right side. That is the concept. But if I understand that somebody is hitting my head from the left side and it goes to the left side as far as deformation is concerned, then probably I am totally wrong. So as an engineer, it is very much essential that the physics of any real life problems must be well understood, and it must be solved in collaboration with the scientists for developing, for analyzing, and for synthesizing, and finally adapting it. So friends, that's much I can say, because I am not deep into this topic. I am a misfit to all of you, those who are group of its here. Otherwise, I would have spoken a little bit. Whatever little bit knowledge I am having, I have shared with you. And I hope the lecture series that you are arranging by contacting speakers of and eminent speakers from IITs and Institute of Physics, NITs, and other places. Our students and research scholars, those who are attending this program, will be highly benefited. TechCube is a medium through which we only give the funding, but the entire responsibility is with the principal and the TechCube group that is available in the institute. All heads of the departments, they are also part and parcel of this program. So I am happy to announce that CET stands as #1 institution as far as expenditure and other status is concerned of the state. And others are following CET to do good things. In fact, Government College of Engineering, Kalahandi, or Varampur, or IIT Sarang, and others, they are following you. So give a good impression to everybody that yes, we are #1 and we must maintain it as #1. Excellent is always excellent. Excellent cannot be accepted that it is the second excellent or third excellence. So that's my request to all of you. It's a good college and people are very good. I love all of you, and at the
in some way or the other. Of course, here we possess most of the time what is called the properties, the physical properties which we come across. Actually, what we encounter is the cooperative phenomena effect. See, I am being practitioner of magnetism, so magnetism is nothing but the cooperative phenomena.
Professor S.M. Yusuf Shah, respected Principal CET, Professor P.K. Patra sir, respected State Project Administrator, SPI Odisha, Professor Antarjami Mishra sir, respected TechCube Coordinator, Professor P.K. Parida sir, respected Basic Science Coordinator, Professor A.N. Acharya sir, respected HOD, Department of Physics, Professor Babita Ujha Madam, respected Professor Devakan Samal, IOP Bhubaneswar, distinguished Professor, students, and all participants. I, on behalf of the Department of Physics and the members of organizing committee, extend a very hearty vote of thanks to the honorable dignitaries who blessed us with their presence and took out valuable time of their busy schedule. I would like to extend our special thanks to Professor S.M. Yusuf, Director IOP, for inspiring us with his vast scientific experience and enlightening the title of the webinar. I would like to express our gratitude to our principal, Professor P.K. Patra sir, for his continued encouragement and support to organize the webinar. I would like to thank State Project Administrator, Professor Antarjami Mishra sir, for his valuable guidance in conducting the webinar under TCube 3 and exchanging his views on linking physics to the technology. I would also like to thank our TCube 3 coordinator, Professor P.K. Parida sir, for his kind support in organizing the webinar under TCube 3 activities. We are very thankful to our basic science coordinator, Professor A. Acharya sir, for his valuable input towards successful organization of this webinar. I am very grateful to Professor Devakant Samal, IOP Bhubaneswar, for providing us an opportunity to organize this webinar in collaboration with IOP Bhubaneswar. I extend my big thanks to our head of the department, Professor Babita Ojha Madam, all the faculties and staff of the department for working tirelessly during this pandemic to make this webinar successful. I also express my sincere thanks to all distinguished professors who are going to deliver their talks in the coming days for making the webinar great success. My heartful thanks to the heads of various departments and the faculties of their valuable suggestions and guidance in organizing this webinar. Last but not the least, I should thank my dear colleague, Dr. Rakesh Ranjan Sahu, for efficiently managing all the web-based activities towards smooth conduct of the webinar. Finally, I would like to thank all the participants who are present here virtually. Thank you. Now, this is the end of our inaugural session. The next session will start just after a few minutes. Now, I would like to request Dr. Professor D. Shamal to chair the session. Thank you.
Now, Professor Yusuf, your talk is ready. Can we? May I ask to Professor Yusuf, is the talk is ready? Can it be now flashed, the title or the first slide?
Yeah, just I'm doing it, yeah.
Okay.
Shitankar.
So, are you facing any problem?
I'm opening it, just,
Okay, now it is opening.
this is a big, large file, that's about. Are you getting my?
No, I see black. I see black. You are presenting to everyone, but it is showing black.
Is it okay now? No?
I can see your desktop, but your slide is a.
This is the point.
Rakesh is there, no?
Yes, sir.
Can
So
you
there is
guide us?
problem in actually there is a Google Chrome is open, so that will be minimized. Then PPT will be will show.
Okay, yeah. Please guide us, because what is to be done.
Sir, please present your screen first.
Yeah, now he has presented.
Okay. So now minimize the Google Chrome.
Sorry.
He is telling to
Sir, please
minimize.
your Google Chrome browser. Sir, please minimize your browser.
I'm doing it.
So there is a top right top corner. There is a cross symbol. Then there is a minus symbol is there. Just click on that minus symbol. Yes, sir. Yes, sir.
Yeah, but
So
now
click
it's
on, and so sir, click on present now. Then there is an option. There is a full screen, entire screen.
yeah, I did that. But
Yes. Your entire
Permanent.
screen. Click on that your entire screen, and then minimize the browser. And then
no, I
PPT.
did all those.
Yes.
I'll just, I'll just log out and
Yeah, maybe
because
that's.
there are many, because I have this virtual, that is the whole problem.
Please hold on for a couple of minutes because I think Professor Yusuf is logging in again.
Okay, sir. Waiting.
Come on. Sir, are you back? Yeah.
Is it okay now?
Yeah, you can maximize maybe, or it is okay. I think it's okay.
Oh, I can,
You can maximize probably.
yeah.
All right.
No, wait. Let's. Is it okay now?
It is coming. Yes, it is fine. Thank you.
No, sorry, because we have the virtual machine.
Yeah, okay.
That's all this problem, because as such it is not permitted from here, and we need to go to virtual machine and okay, sorry, okay.
Okay. So yeah.
Lost some time.
Yeah, so let me now introduce. So I'm very glad and honored to introduce today's speaker, Professor S.M. Yusuf. In fact, I know Professor Yusuf for a long time because even I collaborated during my PhD, but now he is the Director Institute of Physics. He's the Director Institute of Physics, and currently he is the outstanding scientist and the Associate Director, Physics Group of BRC Bombay, and also simultaneously is acting as a Director Institute of Physics Bhubaneswar. He is a Senior Professor in Homi Bhabha National Institute and Dean Students Affairs, Homi Bhabha National Institute, BRC. And his research experience and expertise mainly focuses on advanced magnetic materials, neutron scattering. And he has worked on various fields, but as I mentioned, the focus is on extensively in the area of quantum magnetism, low dimensional magnetism, the phenomenon of various magnetic effects, magnetic proximity effects, and molecular magnetism. As you was mentioning, he tries to understand the spin physics in molecules or in solids. And he has published many papers throughout his career. He has a very illustrious career. And he not only the publication, he has also obtained a patent, one from United States and as well as one from Europe. And he has, to his credit, many awards and accolades. I will not detail out the everything, but I would like to tell that he is awarded with P.K. Iyengar Memorial Award from Indian Physics Association. He has got DI Group Achievement Award, Rajaraman Prize Lecture in Physics, DI Homi Bhabha Science and Technology Award, then MRSI Material Science Annual Prize, NS Satyamurthy Memorial Award, and there are many awards which I will not list it. And he was also the recipient of a United States Department of Energy Fellowship and the Spanish Ministry of Science and Education Fellowship. Presently, he has many responsible positions. He serves as the Vice President of Indian Physics Association, Vice President of Material Research Society of India, President of Neutron Scattering Society of India, and also he serves in various committees of Department of Science Technology, CSIR, UGC, and Department of Atomic Energy. So he is also a member of Neutron Science Review Committee because he was doing his postdoc at Oak Ridge National Laboratory, United States. And also he is also a board member of the Asia Oceania Neutron Scattering Association, Japan. So he has a very illustrious career, and with these few words about him, now I would request Professor Yusuf to deliver his talk, and please enlighten us with the title. The talk title, as I mentioned, he will be talking about magnetism, fundamental and applied aspect of magnetic materials, an overview of current affairs. Thank you very much, Professor Yusuf.
Thank you, Professor Devakanta Samal, for your very kind words and nice introduction. Let me start my talk. As he rightly pointed out, that today I have promised to talk about fundamental and applied aspects of magnetic material and an overview of current activities, or of course, this current activity, what has been going on in my laboratory in Bhabha Atom Research Center. So today's this work basically what we have been carrying out at BRC, though you see I have 3 affiliations here. And again, once again, I thank the organizers, particularly Madam Professor Bobita Oja for the kind invitation. And in our group, over several years, we have been carrying out different aspects of magnetism, magnetic materials. Of course, we mainly do fundamental science and we try to publish the outcome of our research in international peer-reviewed journals. And time to time, we do see some spin-off which has technological relevance. So in today's talk, what I plan to give the flavor of that in areas, some of these areas, what kind of fundamental science we do, and that has led to what kind of applied aspects. So that is what is the approach I will be taking here. In some of my talks I give purely from fundamental, but here it is a little bit other way. So the type of magnetic materials which are of practical importance, technological importance, and which we have been working on, I have listed. These are the activities in our lab, whether it is permanent magnets, whether the large magnetocaloric effect materials, whether it is nanostructure materials, whether it is battery materials, or the spintonics materials, molecular magnetic materials, multiphoric materials, and of course quantum magnets. So that involve the low dimensional magnetic material 1D or 2D. So today, because we have the nuclear research reactor, that is the unique facility in our country. We are fortunate to have this facility because besides the bulk measurements which we do to understand the fundamentals of magnetic materials, this microscopic technique neutron, which comes from the nuclear reactor, we do use very much to understand the physics at the atomic length scale when we talk about the magnetic static properties. And this is one of the recent review articles which we wrote on neutron scattering or advanced magnetic material. So one can see some of the aspects what we have been dealing with, and there one will get to know how neutron scattering is useful for studying magnetic materials. Now, when you talk about the permanent magnets, as you know, their usage is very, very widespread. In all these pictures, what you see everywhere, permanent magnets are used. I don't have to elaborate it. Even the door magnet you have been using. So wide magnetic materials applications in terms of permanent magnets are very, very widespread. As you see in a car, how many places one uses permanent magnets. Now, when you talk about the permanent magnets, what one is referring to, the large BH loop. This BH loop, what you see here, this is basically the energy product. So one needs to have these large values of this. And of course, beyond doubt, this material should have the ferromagnetic or ferrimagnetic property at the temperature when you want to work. So particularly we work at room temperature. So at room temperature should be highly ferromagnetic. That means this Curie temperature, means the disorder paramagnetic to ferromagnetic phase transition temperature should be very, very large. So that kind of material we can use for permanent magnets. And you see historically this area has developed. I have shown there are different kinds of permanent magnets and how much BH this product, that is the energy actually basically it is stored, magnetic energy is stored, and that energy actually one uses basically. So how much energy you can store higher and higher, that is the measure of the how strong the magnet is. And of course it has to work at the working temperature. And here you see the historically same thing. You see how the permanent magnet has been developed over the years, and this BH max, this energy storage capacity. Now, two types of permanent magnets we talk about. One is the soft permanent magnet, where the coercivity is very large. This opening of the loop is very small. And another is a hard magnet, where this loop opening is very large. So both are useful depending upon the requirement. Now, I will only like to say this is the area, of course, it is continuously evolving. New discoveries are always there. People have been looking for new magnets, new magnetic materials, so that this can serve better purpose for the mankind. One such example I am showing, let us say garnets and ferrites for high frequency transformer use, because the ferrites or garnets, they are being oxide materials, they are insulating, so they can use in transformer, so and high frequency application. Here what I am showing, this particular garnet which we have worked on, see the magnetized and magnetic moment as a function of temperature, and it goes to zero at this kind of, this is the temperature in degrees centigrade. So our room temperature is here. This is my room temperature. So the Curie temperature is very, very large. Okay. So this is one good parameter, that at room temperature it is highly magnetic, ferrimagnetic here. And what about the magnetization? This value is also very large, mu Bohr magnetron per formula unit. Here also one can see at 27 degrees centigrade room temperature, depending upon which composition you deal with, the magnetization saturates, of course, at a little high field. That field requirement is very low. 1 kilostate field is of large magnetic moment at room temperature with large Curie temperature are very much suitable, and they are also insulating, so they are very much suitable for this kind of purpose, this transformer application. And if you see the other one, this is a ferrite, lithium iron chromium based ferrite, where you see again the TC is very high, 437 Kelvin. But here what you see, the magnetization as a function of field, and then you look at 310 Kelvin, which is slightly above the room temperature, it is still magnetization is very much there. But you see the hysteresis opening is hardly there. So it only means that it is a soft magnet. So that because soft magnetic property is dictated by this low coercivity, Hc is typically about 100 Oersted. So this kind of materials are still we are working, and as you see that this kind of paper we are able to publish in physical materials or physical or general applied physics. So means development of this kind of permanent magnetic material importance is still there, because this field is still very fertile. But the question is, the example so far what I showed you, those are so-called inorganic materials, inorganic compounds, whether it is ferrites or garnets. Of course, there are tungsten metals, and their density is typically 0.8, 0.7 gram per cc. Now, if you know that when you deal with a transformer, if you ever lifted a transformer, or for that matter your laptop, you always bargain for lighter and lighter laptop, So this magnetic storage devices, these permanent magnets, wherever you use, or even the vehicles, so you always want something should be lighter. Lighter has not only the main purpose is they want something weight is less, it is energy efficient, right? And more handy in case of, let us say, laptop, or it is energy efficient as well. Now the question is how to lower this weight. So one way of deal with, suppose if you get this kind of material, this kind of organic so-called molecular magnet, where you see these oxalate, phenolphthalein, these groups are there, And you see the magnetization function of field, and this kind of, there's a large hysteresis, and of course, this is a low temperature, what I'm showing here hysteresis, but here density, the mass density is very, very less, typically 1 gram per cc. So that means if you can get a permanent magnet out of these molecular magnets, then what will happen? Your mass weight of the magnet will be typically 1 order of magnitude less. So that will be quite attractive. And in this kind of case, what is the observation you see that we have been still working. I have not updated the figures. Even this year also we have published in this very recent paper 2020 is Journal of Physical Chemistry C. Now the corrosivity is 3.2 Tesla, so very large corrosivity, very, very hard magnet, okay? But of course, challenge is this, ordering temperature is low, means what we need to have this room temperature molecular magnets which will act as. See, as you see, we have been working in this area. As you see, lots of papers were published in the area of molecular magnets. The intention is to see find the new molecular properties in terms of magnetism, molecule-based magnetism, and also to look for new magnets which are lightweight magnets with large corrosivity and with extended Curie temperature and so on. For example, here one thing I show you, look at this magnetization curve as a function of magnetic field. It is like, is saturated, also no hysteresis, hardly any hysteresis. So this is a very, very soft magnet. So the first one, which I showed you, molecule-based magnetic it was 3.2 Tesla hysteresis, this corrosivity, very, very hard magnet. But here this one is very, very soft magnet. Both cases density is quite low, and that is a good part. So this is a soft molecular magnets. The previous one is hard molecular magnets. So a lot of research is going on, and future research is very much required to have the stable molecule-based magnets which can be used for practical applications at room temperature. Of course, the search is also there that how to avoid rare earths. So typically rare earth-based permanent magnets are more useful because they can give more energy product, more anisotropy. But how to avoid these rare earths? So that attempt has been going on, and the rare earths we can get only from China. So how to avoid that? So without using rare earth, how can we have better permanent magnets? Now the another topic, second topic, I will be talking about the how this magnetic entropy can be utilized. What is magnetic entropy? Across the magnetic phase transition. So that is what I'll be talking about. Now here, one example I am showing from earlier work, the magnetization scale as a function of temperature. You see there is a magnetic phase transition, and wherever there is a magnetic phase transition, there is a magnetic entropy change across this phase transition. And this magnetic phase transition here, it is below room temperature, but by doing substitution at the cobalt side by iron, we are able to tune the magnetic phase transition temperature from lower towards the room temperature. This is 300 Kelvin. So the tuning of magnetic ordering temperature is possible. So tuning of delta SM, change of magnetic entropy across this phase transition is possible, and you can shift towards room temperature this change of magnetic entropy. So this is another example. For example, the Husser alloy. You see magnetic entropy change as a function of temperature. Sorry, these view graphs are slightly distorted because of I'm using that other other server. So because of that, but nevertheless you can see that. So Husser alloy, you see the change of magnetic entropy over this room temperature is here, and you are able to tune it. This is slightly higher temperature, 340-50 Kelvin, but this is shifts to the lower temperature. So tuning of this possible and relative cooling power, what is the integration over this cold, T cold to T hot, over which, it can operate in a magnetic cooling, as magnetic cooling devices. So T cold to T hot, if you integrate of the change of magnetic entropy at a constant field, so that gives you the relative cooling power. And if you want to use this material for magnetic cooling, then you need to have larger RCP, relative cooling power. And here is another, again, this is magnetic cooling is possible even with the molecular magnets, as you see how with the field, this delta SM can be enhanced. So this kind of possibility. And based on that, we wrote a review article in BRC, our BRC newsletter, and one of my engineer colleague, a friend from other group, they came forward and said, let us make, this is very interesting, and let us make magnetic refrigerator test setup. And this is the engineering drawing. I will not go details into that. So it has got different components, the magnet design, the magnetocaloric effect sample design, mechanical design, control module, thermal hydrolysis design, because the person works in the reactor engineering, reactor heat cycle. So this is the detailed design of this development of magnetic refrigerator test setup in BRC. And this is the detailed engineering design. Is P. Haldar from the reactor engineering division of BRC. Of course, my colleague is also there, Moiz Mukaddam, in this work. Now you see different parts, This is the permanent magnet, and this is what you see here. Inside this magnetocaloric effect material is there, and this magnet can give up to the field. This is actually the magnetocaloric effect material, which that means this material gives large magnetocaloric effect, large magnetic entropy change across its magnetic phase transition temperature, and that is there inside this. So this is a rotating device. So when it goes inside the magnetic field and comes out, then the heating or cooling takes place. Okay, so magnetic cooling is possible because of that. And here, these tubes, what you see, basically to take out the heat. So this is like a exchange through the gas, the heat is taken out. So I'll show that in the next one. This is again engineering drawing of the same thing, and this is the magnetic cooling magnetocaloric effect material in a thin sheet, which I showed you in the previous one. So like this, one by one is stacked, large number, and it is this assembly is inside this, what you see here. Now this is these are the tubes which you see for the taking the heat, and we have done the calculation under 1 Tesla field, how much the magnetic cooling we can get. So delta T is 2.5 Kelvin per Tesla. This is what for the system is gadolinium. And this is the photograph of the test setup. I am audible, right? Professor Samal? Hello?
Yes, sir.
Yeah, because time to time can give little sound, otherwise I'm in black box. So this is the magnetocaloric refrigerator test setup. Yeah. And this is what is the assembly. I see the permanent magnets at 4 places 1, 2, 3, 4, and this is the rotating. So magnetic material is there. The magnetic goes inside. So this is the full assembly, as you see. And how this temperature with the time, see, at this point actually magnetic cooling starts. So, depending upon when you remove the field. Okay, when you remove the field, magnetic cooling starts. So that is what is shown. And here it is again. See, this is a gadolinium based alloy which we made, and we showed that again magnetic cooling is possible. We have published this. Let me see whether this works or not. A virtual system it may not work, No, it will not work there because that is the problem. So sorry, I had to copy in the virtual system, so this not compatible. That is the problem here. Anyway, it doesn't matter. I could have shown you that the temperature is dropping when it is going in the magnetic field. So temperature would have dropped from here like this. Okay, that video was there. That is a recording. So this is the magnetic field. This is the starting temperature, and I could have shown you how the magnetic this temperature, this value 18 point, this how it drops. Now you may say why the starting temperature 18.3, because they are the T cold temperature, and T hot. Depending upon that, you have to design the working temperature range. So magnetic cooling we have demonstrated using this setup. So sorry, I could not show the video because of this virtual machine. Now another example I show you based on the magnetic nanoparticles for biomedical applications. Now we have been working on magnetic nanoparticles, and this is one example, magnetic nanoparticle membrane. And this work we have done with Dr. K.R. Balakrishnan. He is the director of this Fortis Hospital, Chennai. And we have got 2 patents, US patent as well as European patent, both are granted. And of course, my senior colleague, Dr. Chebi, was also there. And these are, see, we have been working on lots of magnetic nanoparticles in the group. So I'll not go into details of the bare nanoparticles or the carbon oxide nanowires, by the core cell kind of nanoparticles, by the 2D nano wafers or nano flower, we have been all working on. This is like a capacitance, This is a nano capacitor, because you can imagine between 2 plates, it will act as a capacitor. It is a nano wafer. But for this purpose, let us say when you have nanoparticle of this diameter, diameter is typically 10 nanometer. And by doing neutron diffraction, magnetization at room temperature, neutron diffraction and room temperature, we have shown that they're highly magnetic. If the nanoparticles are means that should have been the intensity. But this additional intensity of this 111 Bragg peak tells that it is highly magnetic. So DC magnetics also tells that it is a Langmuir function kind of behavior. Each magnetic nanoparticle carries 28,000 Bohr magneton, huge moment. Okay, and this kind of nanoparticles, we have loaded in medical grade polyurethane, and we have made the magnetic membranes. And these membranes, as you see, can have different shapes and size. We made it, we have characterized it, and then we have used and demonstrated that these magnetic membranes can be used for medical. This is one picture I got from the surgeon. See, when the heart patient, for heart patient, when the heart totally fails, at present, what is there? The pneumatic valve. Pneumatic valve means basically patient has to be in the hospital, and these pipelines, helium gas is passed through, helium cylinder is kept, helium gas is passed through, and this artificial heart is run by that. So whatever, the patient cannot go home, and also this sorry, I got cold. And this patient, of course, can survive in a hospital, but main problem is that since these cables pass through the chest, so that causes the major infection. Patient cannot go home, patient cannot take bath, and patient invariably dies because of the infection, though the heart is functional artificially. Now the question is, the problem to us, can we have a machine which will be put inside the body, but it will be operated from outside without having any physical connectivity through these cables, So that is possible by magnetic means, electromagnetic force, as you know. That's why the magnetic membranes are handy. Here, again, this video may not work because of same reason. So I could have demonstrated here that this magnetic membrane, under the action of this, under the action of the magnetic field, to and fro motion is possible. So this magnetic membrane is capable of displacing the fluid, displacing the blood under the action of the magnetic field at room temperature. That is what is demonstrated. And this device is made, so basically magnetic membrane is here, so it can have two under this magnetic field, it can go to this position or this position, so it can either pump in blood or push blood, so suck in or suck out. So this is possible by this magnetically actuated pump, so displacement pump. Of course, this kind of magnetic membrane, in the patent we have also shown that this can be used for other purposes. For example, this, if the urinary bladder, it can act as a valve, artificial urinary sphincter, that is possible, or even for human body when this somehow gets paralyzed, then also it can be used in this kind of applications. Of course, following that patent, being in BRC, a team was formed by Director BRC, and there some are engineers, some are robotics engineers, one or two metallurgists, one chemist, and to make this artificial uranium sphincter and this is the 3D print, what you see here. And finally, we have made this one when the patient cannot pass urine, particularly it happens at a later age. And this is the device which you have made, which is suitable to male organs. I'll show you how. See, it is essentially like this. So this you can imagine that if this kind of, it is very tiny and very light. We have made with that's a metallurgist was required, very, very light atoms we have used. And so that this in a male organ, when male cannot pass urine in normal way, this can go. And this is, let's say, this flow of fluid will be through this, and you will see how it can, in normal state, it will be closed, and because it has to be done surgical means. And by the way, for that we had to have close interaction with the doctors from our BRC hospital as well as Mumbai doctor to make this device, because this has to be compatible. So the tube which you see, this is used in medical hospitals because its stiffness would be matching with the organ, the male organ. Okay, and so how much pressure it has to, magnetic force it has to apply. So again, the video may not work. So let me see, because same problem. So I'll see here, what you see here in this case, actually, you see the closed one. Actually, I cannot show the video. I have a separate video, but it will not work. So under the action of magnetic field, what happens? It opens up. Okay. So that means when patient has to pass urine, one has to simply take out a small bar magnet from his pocket and bring to this device, and simply this will open up and patient can pass urine, and after the job is done, the patient can take the magnet, bar magnet out, small bar magnet. This is what is the magnet actually. And then it will be closed. So normal state is closed. So this is one example I could show. We have been working on other kinds of materials as well. For example, this is one magnetic phenomenon we have studied, which is known as the negative magnetization. So this is, of course, we have been studying, and these later references are somehow, it has not come in this virtual machine. We have published 3-4 papers even this year itself. We wrote a fantastic first review article on this phenomenon to establish that this is a genuine phenomenon in physics reports and so on. And basically here, what we are talking about, this kind of effect, the magnetization, as you know, in a paramagnetic state, when you go to magnetic order state, magnetization develops. Now, magnetization by definition, as you know, the moment along the applied magnetic field. Now the question is, in certain cases, you see the magnetic moment is anti-parallel to the applied field. Magnetic moment is not parallel to the applied field, but rather anti-parallel. So that means what you measure, so-called magnetization with a negative value. So how does it happen? Here, actually, the measured magnetization as a function of temperature, you see magnetization is the negative side. For this compound, magnetization is on negative side, magnetization is on the negative side, magnetization is on the negative side for various compounds. So this is called the change of magnetic polarity from the positive to negative as a function of temperature. Of course, this is done at moderate magnetic field. So change of polarity. And it means it can give us two magnetic states, this so-called minus state and plus state. So bistable magnetic states are possible with this kind of magnetic materials, and that can be used in this kind of thermally assisted magnetic random access memory. And it is very, so you can imagine that, of course, the other ingredient what one needs to use here called exchange bias, that also we have worked on. So this kind of material will be very, very useful for practical applications in the area of spintonics, which I will not elaborate, but one can see the review interested in knowing more about it. So I'll give now my last example, that though we have been working on several classes of materials, but in the limited time, I thought few examples. This is another material, the Garnet material, where Garnet material, the ordering temperature Tc is very, very high. This is in degrees centigrade. But here what is there, the oxygen conduction, the oxide ion conduction, it takes place. And I will show you in the next view graph. You see the oxygen ion conductivity basically, but it is coming from the oxygen ions. And you see this is in log scale, and you see how conductivity increases. How conductivity increases. See this kind of conductivity variation at room temperature 10⁻⁻10, this scale, room temperature here, to 10⁻², 450 degrees centigrade, Siemens per centimeter. So this kind of variation of conductivity. So that means this material is very, very suitable for this ionic conduction applications, oxygen conduction applications, and we have done the detailed analysis. I am not going to that. This is nothing but the RNS kind of conduction of these oxygen ions. So, but one point I must tell you, that this kind of material, so it is applicable for solid oxide fuel cell kind of oxygen conduction, but it can operate, normally those solid oxide fuel cells, they operate above 900 or 1000 degrees centigrade, but it can operate at as low as 450 degrees centigrade. So this is a big bonus, in the sense the machine can be operated at a much lower temperature, so it is much energy efficient and so on. And of course, by doing powerful Newton diffraction experiment, this is what we have obtained by doing Newton diffraction experiment, that how these oxygen ions, they conduct in the lattice. So these paths, so these paths we have found out, that how oxygens can pass through in the lattice, what is their path. So this is called the oxygen ion conduction pathways. The bond van valence sum approach of this Newton diffraction data, by that we have shown this. In fact, we have been doing similar analysis by using Newton diffraction data. Recently, we have been working on sodium-based layered structure, where the sodium is there in the these are the sodium. These are the sodium. Here you see the crystal structure is the layered structure. This is the crystallographic C-axis. This is our AB plane. So this is the AB plane, but crystallographic C-axis. So sodium ions are there in the AB plane. And so this is the layered structure. And the sodium ions are very much mobile. And this is a recent paper. So we have applied the same methodology and shown how the sodium ions are conducting in the lattice from the Newton diffraction data analysis. So with this, I think I gave examples that from some of our recent work, which we have been pursuing over some years, that in the area of permanent magnets, in the area of large magnetochromatic effect material that can be used for magnetic cooling. So I can say so far what we have achieved for large magnetocaloric effect material, not that we have made a device by using, we can test different kinds of magnetic material which have potential for magnetic cooling, and we can measure actually how much cooling effect is there, so that we can up to maximum under 1 Tesla field. So we can demonstrate. So we call it test device, magnetic cooling test device. So eventually this can be transformed to the magnetic refrigerator, and that will be a replacement of this gas-based refrigerator which we use in our day-to-day life. But for the time being, what we have, the test device for testing the magnetic cooling effect. And as far as permanent magnets are concerned, it is the ongoing process to look for particularly the molecule-based magnets, and we can look for low density, nearly 1 order of magnitude lower magnets, either we can have, which will work at room temperature. So nanostructure materials, I showed one application here, that magnetic membranes, and that can have medical applications. And battery materials like sodium, conductivity, I just showed. Of course, I have not. One hint I gave from spintronics material point of view, that states. Hello? Yeah. Two magnetic states, the positive and negative, how they are useful for getting the bistable magnetic states for magnetic decoding. I didn't go to quantum magnets and multifluidics and so on. So with this, let me thank my collaborators, MD Mukaddam, P. Haldar. P. Haldar is the engineer who has designed this theater. D. Bhosle, my earlier student from Pune University. My colleague Amit Kumar, this is the sergeant with whom we work on the magnetic membrane, and my earlier senior colleague, Dr. Yakmi, and Dr. R. Tiwari. Then later on, he was who was very much there for this device, which can be used when the patient cannot pass urine, and for that this small device which you have already made. With this, I thank all of you for your kind attention. Thank you so much.
Thank you very much, Professor Ishu. Now we'll be taking I see some of the questions are already in the chat box. So I will read out the questions for you. So let me start from the bottom. That I can see there are 2-3 questions. So one question one student has asked, I think, for magnetic cooling, are the magnets used are hard or soft magnetic materials?
For magnetic cooling, no. For magnetic cooling, for magnetic refrigerator purpose, in my presentation from the basic research, I have showed that as you increase the applied magnetic field, when a material is undergoing magnetic phase transition from the disordered paramagnetic state to the ordered ferromagnetic or ferrimagnetic state, and if you do the measurement under higher and higher magnetic field, you get larger magnetic entropy change. So your requirement would be to use magnet which can give larger magnetic field. But the application which I showed, the device which I showed, test device, there we have used permanent magnet and it gives maximum 1 Tesla magnetic field, because if you have to make a magnetic device, the magnetic refrigerator, if you have to use at home, neither you can use superconducting magnet or electromagnet will be more cumbersome. So permanent magnets, even 1 Tesla kind of field is good enough to give reasonable magnetic cooling. That is what is our approach. So answer to short question is that you need higher magnetic field. Short answer to your question.
Okay, I think that answers the question from Sairam Ithinari. And now another question from Suraj Ranjan Sahu. He has asked, when you are talking about the artificial heart and artificial membrane, his question is, those kind of artificial organs can be affected by strong electromagnetic field that causes malfunctions. How this situation can be avoided when you use this kind of artificial heart or any kind of artificial organs?
Yeah, I mean, limitation is always there. For example, you have seen that heart patient who are using this pacemaker, they are asked not to go too close to the strong magnetic field. And in a magnetic laboratory, you have seen there is a symbol that, danger. So that kind of limitations are always there. But as you know, the magnetic field, even if so-called strong magnetic field, how it decays as a function of distance. So if you are just 1 meter away, you are more or less safe, But if you are almost like touching it, then of course, if one is using that kind of device inside a body, so one has to be careful. So that limitation. But the advantage is that this kind of devices, once it is made, once it is implanted inside, so it is one time, and then patient can carry this permanent magnet, which has to work in a bag, in a belt, and it is easily doable. So that is this is a more handy, and this is less cumbersome. Unlike the example which I showed, patient has to be in a hospital, the cables need to go through chest, connectivity is there, all the time the helium gas is connected and so on. So those things can be avoided.
All right, so that answers SR South's question. Now there is a question from Joy Krishna Khatai, who is one of the organizers of this, and his question is, what is the maximum magnetic field we can get from molecular magnets?
Yeah, this molecular magnet, the examples which I showed, for example, I think showed 2 examples. The magnetic field what you can get, it is quite good, comparable to the inorganic magnets, but the challenge is only one-fold, that is magnetic ordering temperature, the TC, QD temperature is much below room temperature, because there the magnetic exchange, effective magnetic exchange interaction is effectively very weak. As a result, the TC, the QD temperature is much below room temperature. So if we can enhance the QD temperature, then job is done. So magnetic force will be good enough. From those 2 examples, that was very much apparent. So challenge is on the enhancement of how to increase this TC, QD temperature, not on the net magnetic field or net magnetic induction. Okay.
Okay, I think Dr. Khatai has got his answer. And there is one more question. By using artificial organs, is it safe for patients during MRI scanning instrument?
Yeah, no, as I said, when any patient, when one is carrying out this kind of devices, which can get affected by magnetic forces, so one one will be limited to those kind of. For MRI, as you know, there also again it is driven by magnetic force. So one will have that limitation definitely. Yes. So if patient over and above that kind of problem, patient has to undergo MRI. Okay, as you know that one may not have all the all the medical problems simultaneously, but if one is, then doctors need to take care to execute the second one. That limitation is there definitely. But those are all special cases. One should not be that much unlucky to have all problems together. If one is, then doctors need to take care.
Yeah, I think we don't have more questions. I cannot see in the chat box. So so we should thank Professor Yusuf for enlightening us on this on the fundamental as well as applied aspect of magnetism, where he illustrated us how these magnetic materials can be used in the medical science, how it can be used for cryogenic, and how it can be used for data storage, and how he gave a he scanned over a various kind of materials, starting from inorganic oxide, and how this ionic conduction through oxygen. So I think the students and the participants as well as the researchers who are attending, they had they got some idea on this broad overview of the current activities in the fundamental and applied aspect of magnetism. We thank you very much, sir, for illuminating us on this particular subject. Thank you very much.
Thank you. I add here that I selected this topic thinking that I am dealing with more on engineering friends on the other side CET, and of course most of them with physics background, but in the engineering history, at least if they can get motivated that even using the basic physics principle, how one can I thought of designing my talk in this direction, but I apologize that 3-4 these movies I had, which because of this, had I spoken from home or somewhere else, I would have shown those movies, how this urine can be stopped by magnetic means, you passing urine, or how this magnetic membrane can be oscillated under magnetic field. Those movies I missed here. Anyway, nevertheless, I think I made a point. And I thank you so much, and thank you, Professor Samal.
Thank you very much, sir. I think this session is.
Thank you.
Yeah, I think this session has ended.
Yeah, thank you.
Yeah, thank you.